So this video clip is all about travel graphs. Okay, so distance time graphs, speed time graphs. So this first question here states that Arshad delivers parcels on his bike. He starts from his home. Here's the travel graph for the first 40 minutes of his journey. And the first part of the question is, what time did he start his journey? So this is for 1 mark. So quite simply, just look at the scale here along the bottom, which indicates its time. So clearly he started his journey at 1300. So you just put 1300 for 1 mark. Second question says he had to stop to deliver each parcel. How long in minutes did his first stop take? So if you look at where the line rises to, so here he's travelling away from home. As soon as the line is horizontal, that means he's no longer travelling away from home. Okay, so he stopped for his journey at exactly 1305. You can see there from the scale, it's halfway between 1300 and 1310. So 1305 and then till 1310. So that's exactly 5 minutes. Okay, so that's those parts of the question there. Part C. What is the distance between the two stops shown on the travel graph? So the distance between this horizontal line and this horizontal line. Well, the distance is given along the vertical axis, the y-axis here. So you can see here he was 2 kilometers away from home, and here he was 0.6 kilometers away from home. Just look at the scale there. I'll zoom in, probably see it easier. Okay, so 2 kilometers, 0.6 kilometers. So that is a difference of 1.4 kilometers between those two stops. The answer here is 1.4 kilometers. Okay. The last part of the question. At 1340, Arshad stopped for 10 minutes to deliver his last parcel. He then cycled home at a steady speed. He got home at 14:15. Complete the travel graph to show this information. So if he got home at 14:15, then you must know that the line finishes at 14:15. So you can put a cross straight away here on the graph. What you can also do is you can put a horizontal line representing 10 minutes at 1340. So at 1340, 10 minutes he'd stopped. Okay, so that's a horizontal line which finishes at 1350. Then you draw a line segment from 1350 straight through to 1415, again with a ruler and using a pencil, and that there is the travel graph finished. So that whole question there is 6 marks. Question 2. On Monday, Ria delivered a parcel to a hospital. The travel graph represents her journey to the hospital. And it also says that she left home at 1300. She drove for 30 minutes at a constant speed of 40 miles per hour. She then stopped for a break, and she then drove to the hospital at a constant speed again. She was at the hospital for 30 minutes, and she drove home at a constant speed of 32 miles per hour. Show that she does not arrive home before 16:30. So the way that we're going to do this is, first of all, I'm going to label as much of this graph, the axes, as possible. Okay, so let's start doing that now. So you can see here, since she left home at 1300, I'm putting 1300 here, and it says that she drove for 30 minutes at a constant speed. So this line segment here must represent 30 minutes. So that's why I know that 30 minutes, this must be 1330. So this represents half an hour, this must be another half an hour, so that's 1400. So I can label all these times along here, along the bottom axis. Okay, I also know that she drove at a constant speed of 40 miles per hour. So if she drove at 40 miles per hour in this part of the journey here, then in half an hour, she would have covered 20 miles. Okay, so 40 miles per hour. So in 1 hour, she would have covered 40 miles. So in half an hour, she's covered 20 miles. So now I can label this y-axis with 20 miles here. And since that's 20 miles, same distance up the axis must be 40 miles. So I've labelled my axes, I've numbered them, so I know the scale now. Okay, the next part is here. She's at the hospital for 30 minutes. So she's at the hospital for 30 minutes, so obviously she's not driving there. She's not getting any further away from home. So that's a horizontal line segment. So for 30 minutes, from 1500 to 1530, it's a horizontal line here. Show that she does not arrive at home before 1630. Well, if she's going to get home at 1630 and she's leaving at 1530, that means she needs to get home in an hour. To get home in an hour, she needs to travel this distance in 1 hour. She needs to travel 40 miles per hour. If she travels at 40 miles per hour, she'll get home just in time. But she drove home at 32 miles per hour. Therefore, you can see she didn't drive fast enough to get home before 1630. And that's what I put in my sentence here at the bottom. Okay, so that question there, the whole question is worth 4 marks. Question 3. Steve drove from his home to his friend's house. He stayed at his friend's house and then drove home. Here is Steve's travel graph. So you can see there a travel graph. You've got the distance, you've got the time. This clearly represents his outward journey. That's where he stayed at his friend's house, and that's his inward journey. So the question is, underneath, part A, for how many minutes did he stay at his friend's house? So you can see he stayed at his friend's house from this point on the axis here till 1330. Well, this point you can see is exactly halfway between 12:30 and 1 o'clock. So that must represent 12:45. 12:45 until 13:30 is 45 minutes. So clearly that there is 45 minutes, that horizontal line there where it's stationary. The next part of the question states, what was Steve's average speed on his journey home? The average speed on his journey home. Well, to find the speed, you need to do the distance divided by the time. The distance divided by time. Okay, and it wants it in kilometers per hour. So we need to turn this time into hours. The distance is straightforward. The distance is 25 kilometers, but the time is half an hour. So it's 25 kilometers in half an hour. 25 kilometers in half an hour. So 25 divided by 0.5. 25 divided by 0.5. Without a calculator, I can quite simply find an equivalent fraction to this, which is easier to work out. And so I can just multiply the top by 2, multiply the denominator by 2. That gives me 50 over 1. 50 divided by 1 is just 50. So it must have travelled at 50 kilometers per hour. So that whole question there is 3 marks. So question 4. You're given here a speed time graph for a car journey. This is not a distance time graph, it's a speed time graph. So this represents the speed. So the speed here, the car is clearly accelerating, so it's getting faster and faster and faster. It reaches its top speed after 20 seconds. It stays at that top speed, a cruising speed. And then after 60 seconds in total, it starts decelerating, getting slower and slower and slower until it comes to a stop. So at this point, the speed is 0, and at this point, the speed is 0. So that's where the car is stationary. That's different from a distance time graph, which you've seen in the previous questions. So I'm told that the car journey took 100 seconds, and I'm told that the car travelled 1.75 kilometers in the 100 seconds. Okay. So I need to work out the value of V. And V, you can see from the graph, is the highest speed that it attained, so the maximum speed, that cruising speed. Okay, so to find that value of V, what I can do is I can find the distance represented by the whole graph. The distance represented by the whole graph, okay, is the area underneath this whole graph. So all this combined area, that is the distance. And since I'm told the distance is 1.75 kilometers, I can now find the measurements on this graph. I can find the height of this graph. So let's do that now. So quite simply, let's convert this distance into meters. So instead of using 1.75 kilometers, I'm going to use 1,750 meters. So multiply that by 1,000. Okay. Now, I don't know V here. So what I'm going to do, I'm just going to find the area of this triangle with this speed of V. The area of the triangle is base times height divided by 2. So it's 20 times V divided by 2, which is 10V. The area of the rectangle is the length times the height. The length is 40 and the height is V, so 40V. And the area of this triangle, again, base times height divided by 2. So the base is 40, the height is V, divide that by 2, I'll get 20V. So the total area is 10V, add 40V, add 20V. So that's 70V. So the distance of 1,750 is the same as 70V. So to find the value of V, I just solve this equation. I'm going to divide both sides by 70. Okay, so divide both sides by 70. So 1,750 divided by 70. So to work this out without a calculator is not straightforward. So I'm going to find an equivalent fraction. So in other words, I'm going to divide the numerator and denominator by 10 to give 175 divided by 7. 175 divided by 7, I can just use short division. That gives me 25, and it's in meters per second. It's in meters per second because I could turn this into meters and divided by seconds. So that is your answer there for that first part of the question, and that's worth 3 marks. The second part of the question, part B, describe the acceleration of the car for each part of this journey, and that's 2 marks. So describe the acceleration. Okay, well, you can see the acceleration, okay, of this car is given by the gradient. Since this is a speed time graph, it's given by the gradient. So the steeper the line, the greater the acceleration. Okay, so the acceleration, you can see, was greatest at the starting point part of the journey, since that's where the line is steepest. This last part of the journey here, the acceleration, or rather the deceleration, wasn't as great, since the line isn't as steep. And to actually give values for the acceleration, we need to find the gradient. The gradient is given by the y distance divided by the x distance. Okay, so let's work that out. So I've put here, the acceleration was greatest during the first 20 seconds. Okay, and it was constant at 1.25 meters per second squared. The way I've worked that out, I've done the y distance, for the gradient, the y distance, which is 25 divided by 20. 25 divided by 20 is 1.25. The acceleration was 0 here, since it didn't accelerate at all, because it stayed at that speed. And then it decelerated here, so it went from 25 meters per second down to 0 in 40 seconds. So that's a deceleration of 0.625 meters per second squared. Okay, so if you're not sure on how we've done this, okay, just bear in mind this question involves acceleration from a speed time graph. Okay, acceleration from a speed time graph, and you need some decent knowledge on how to find gradients of lines from straight line graphs. So make sure you watch my clip on my YouTube channel on straight line graphs. So the next set of questions are all calculator questions. Question 5. At 9 AM, Bradley began a journey on his bike. You can see the times there and the average speed, and then also the second part of his journey and the distance covered. So this question, I need to use this information and draw a series of straight line segments on my graph. So the first thing I'm going to do is I'm going to use the fact that he cycled 15 kilometers per hour. Okay, so using a pencil and a ruler, imagine from 9 AM, if he cycled 15 kilometers per hour, after 1 hour he would have cycled 15 kilometers away from home. So that line represents 15 kilometers in 1 hour. But of course he only cycled for 36 minutes, as it tells you here. So anything after 36 minutes will rub out. So you'd rub out this brown section of the line here. The only part of the line that would be left with this blue section. The second part of the journey states that from 9:36 till 10:45 he cycled 8 kilometers more. So he cycled 8 kilometers. Well, here you can see from the axis here, he cycled 9 kilometers. So another 8 kilometers from there would be up to 17 kilometers, because 9 add 8 is 17. And also, he finished that part of the journey at 10:45. So that line segment would finish at 10:45. So that is where you'd put a cross and you join a straight line with a ruler from there to there. The second part of this question, okay, states that from 10:45 till 11, he cycled at an average speed of 18 kilometers per hour. Work out the distance he cycled from 10:45 to 11. Well, he cycled at 18 kilometers per hour, okay, but he only did that for a quarter of an hour. So using speed equals distance divided by time and rearranging it, I'll get distance equals speed times time. So the speed, 18 kilometers per hour, the time is a quarter of an hour or 0.25, multiply them together and I get 4.5 kilometers. So that's the distance he travelled. That whole question there is worth 5 marks. Question 6. So again, a calculator allowed on this question. Here's a part of a distance time graph for a car's journey. So here you can see a distance time graph for a car's journey. Between which two times does the car travel at its greatest speed? Okay, well, the time is along the axis here and the distance is along the y-axis. So the speed we know is given by distance divided by time. So that's going to be this axis divided by this axis. In other words, it's the gradient, the y divided by x. So it's a gradient. So look at which part of this graph is a gradient the greatest. Where is it? Where are the lines the steepest? You can see this is the steepest section of the graph. So the time is between 0 and 20 seconds. So that is your answer for that part of the question there. The gradient is steepest. Work out the greatest speed. Well, the speed is given by distance divided by time. The distance, you can see from here, look at the scale, is 360. Okay, so measure that really carefully. And then the time is 20 seconds. So 360 divided by 20 is 18 meters per second. 18 meters per second. The whole question there is worth 3 marks. Question 7. The distance time graph shows information about a car's journey. So here you can see this is not a straight line anymore, it's a curve. Okay. Use the graph to estimate the speed of the car at time 5 seconds. So remember, speed is given by distance divided by time. So on a distance time graph, it's given by the gradient at that point. So I need to find the gradient at this point. So to find the gradient at this point, I'm going to draw a tangent to the curve at that point. Okay, once I've found that tangent there, I'm going to find the gradient of that tangent. That gives me the gradient of the curve at exactly that point. The gradient is given by the y distance divided by the x distance. So that's for this triangle here, that's 60 divided by 4, which is 15 meters per second. Okay, because it's meters per second. The whole question there is worth 3 marks. Okay, question 8. The graph shows information about part of a cyclist's journey. And what I'm asked to find out is an estimate of the speed in meters per second of the cyclist at time 6 seconds. This is very similar to the previous question. What I need to do is I need to draw a tangent to this curve at 6 seconds and find the gradient of that tangent. So let's do that now. So here you can see I'm drawing a tangent to the curve. It's a right angle triangle, so to find the gradient, quite simply do the height divided by the base. The height you can see is 20, it's the full height of that graph, and the base is 6. So y divided by x is 20 divided by 6. and that is 3.3. And it's meters per second, since I've done meters, divided by seconds. 3.3 recurring, and that is 3 marks. Question 9. So here's a speed time graph for a train journey between two stations. The journey took 100 seconds. Calculate the time taken by the train to travel half the distance between the two stations. And I've got to show all my working out. So this first part of the question is worth 4 marks. Okay, so essentially what I need to do is I need to find the distance, okay, underneath this graph. Okay, so that's essentially the area underneath the graph, and that would represent the distance the train travelled. Then I'd divide that by 2 to find half the distance, and I'd work out the time taken. So let's do that now. So the first thing I'm going to do, we're going to find the scale to find the height of this shape. Okay, this shape, the height of it is 12, you can see from the scale there. And then let's split this shape up into 2 triangles and a rectangle. The base of this triangle is 30, since it's halfway between 20 and 40. Okay, so now I can find the area of this triangle, since I've got the base and the height, and that would give me base times height divided by 2, which is 180. The area of this rectangle is the width of the rectangle times by the height. The width is 50 and the height is 12. That's 600. And the area of this triangle, base times height divided by 2. The base you can see is 20 and the height is 12. 20 times 12 divided by 2 is 120. So the distance is the total area under the graph, which is 180, add 600, add 120. So that there is 900. Now, the time taken to travel half the distance, so half the distance would be 450 meters. So at what point, okay, do we need to find 450 meters? Well, 450, okay, meters, subtract the 180 meters which are travelled in the first 30 seconds, would leave 270 meters left to travel. So I've travelled 180 meters here. I've got another 270 meters left to travel before I'm halfway between the two stations. So travelling 270 meters at a speed of 12 meters per second. So to find the time, I'm just going to use the formula of time equals distance divided by speed. So the distance is 270 divided by the speed of 12, so that would be 22.5 seconds. Now that 22.5 seconds just represents this part of the journey. I've still got to remember that I need to add the 30 seconds here. So 30 add 22.5 would be 52.5 seconds for 4 marks. So the second part of this question, part B, and it asked me to compare the acceleration of the train during the first part of its journey with the acceleration of the train during the last part of its journey. Now the acceleration is given by the change in speed divided by time. The change in speed divided by time. Okay? In other words, it's the gradient of the speed time line segments. Okay? Well, the first part of this journey, okay, the first part of the journey, the gradient of this is given by the change in y, so the y distance, which is 12, divided by the x distance, which is 30. So 12 divided by 30 would give me 0.4 meters per second squared. The second part of the journey, it's obviously a deceleration, so it's negative, but regardless, it's 12 meters per second as the y distance divided by 20 seconds this time, so it's 12 divided by 20, which is 0.6 meters per second. It's negative because it's a deceleration. So you can say that the deceleration at the second part of the journey was slightly greater than the acceleration. Okay, and you can see that because this line is slightly steeper than this line. It's slightly more steep, the gradient is slightly higher. Okay, so that is the answer for that part B. That's only 1 mark, but the whole question overall is worth 5 marks. Question 10. Carol runs in a race. The graph shows the speed in meters per second, t seconds after the start of the race. Calculate an estimate for the gradient of the graph when t equals 4. You must show how you get your answer. So an estimate for the gradient of the graph when t equals 4. Well, quite simply what I do is, again, I draw, like similar questions previously, I draw a tangent to the curve at time 4. So I've drawn a tangent there. Then what I do is I find the gradient of that. The gradient is the y distance divided by the x distance. So the vertical height divided by the base of the triangle, which is 7.5 divided by 7. Okay, and it says an estimate, so roughly that's 7.7 divided by 7, which is roughly 1.1 meters per second squared. The second part of the question asks me, what does part A represent? So part A represents the acceleration at that point in time. That's acceleration at that point in time for Carol running in that race. Okay, so that is part B. Part C, explain why your answer to part A is only an estimate. Okay, so it's only an estimate because, quite simply, my calculation dependent on my tangent, and I can draw my tangent. Depends on how I draw it. You know, it's not exactly perfect, right? So I can draw it slightly differently. So that would affect the height, but also the base of this triangle. The height may be slightly different. The base may be slightly different. Okay, so that's why this is really just an estimate. Okay, so that whole question there is worth 6 marks. Okay, question 11 states that a car moves from rest. The graph gives information about the speed in v meters per second of the car t seconds after it starts to move. So you can see on the y-axis you've got the speed, and on the x-axis you've got the time. So it's a speed time graph. And so part A, for the first 3 marks, it asks for the estimate of the gradient at the graph at t equals 15. Okay, so the gradient, remember, is a change in y divided by the change in x. So when t equals 15, so you go across this axis to 15, you go up, and so at this point you draw the gradient, the tangent of the line, and find the gradient of that tangent. Okay, this is how you do it. So quite simply, at that point, t equals 15, okay, you draw a straight line which just touches the graph at that point. Okay, and then you draw a right angle triangle at any point on that line. Okay, and you measure the y distance, measure the x distance, okay, read off the values, and divide them through. Okay, so the gradient, the way I've drawn it, would be 19, which is the y distance, divided by 24, which is the x values there, and that would give you, with the calculator, 0.8 meters per second squared. Okay, and so the second part of the question asks what that answer represents. Okay. Well, that answer represents the acceleration at that instant, because this is the rate of change of the speed, the rate of change of the speed. Okay, so how the speed changes is defined by the acceleration, right? So that's called the acceleration. Part B, work out an estimate for the distance the car travels in the first 20 seconds of its journey. Okay, so the distance the car travels in the first 20 seconds of the journey. Now, since this is a speed time graph, the distance it travels is represented by the area underneath this curve, so the area underneath the curve. And in the first 20 seconds, that's this section here. So the area underneath the curve in those first 20 seconds is given by these 4 strips here. Now, it's only an estimate, since I'm going to treat each of these strips as either triangles or trapezia. Okay, so let's look at this first one here. Well, that one is just a triangle. Okay, so section A is just a triangle here. So the area of a triangle we know is base times height divided by 2. So the base is 5, the height is 4, so 5 times 4 divided by 2. So the area of that first section there, you can see, is 10. Now the second section here, you can see this shape is a trapezium. So this is why this is called the trapezium rule, right? So we're going to find the area of this trapezium. To find the area of a trapezium, if you're not sure on how to do that, look at the booklet on mathsupgrade.co.uk on areas of shapes, or look at the clip on my YouTube channel. But essentially, you're going to add the parallel sides, add these two parallel sides, divide that by 2, and then multiply by the distance between them, the perpendicular distance here. Okay, so in other words, you're finding the average, the mean average of these two parallel sides, and multiplying by the perpendicular distance here. So that would give you 12, which is that distance there, and 4. Add those together. 12 add 4 is 16, divided by 2, which is 8, and multiply by the distance between them, which is 5. So that would give you 40. In a similar way, you can do it for section C and D as well. Okay, so section C and D, I've done that there. Now, the total distance the car travels in the first 20 seconds is given by the first 5 seconds, 10 seconds, 15 and 20. So all those 4 sections, the areas underneath those 4 sections added up, and that is 220 meters. Okay, and that's for 3 marks. So the whole question there is worth 7 marks. Question 12. The graph shows the speed of a car in meters per second during the first 20 seconds of a journey. So you can see this graph here, it's a speed time graph. Speed on the y-axis, time on the x-axis. So similar to the last few questions. Part A asks us to find an estimate for the distance the car travelled in the first 20 seconds. Okay, and it asks us to use 4 strips of equal width. Okay, so similar to the last question here. Okay, we need to find the area underneath the graph. The area underneath the graph. And we're going to use 4 strips of equal width. Since it's asking for 20 seconds, 20 divided by 4 strips, each strip will be 5 seconds wide. Okay, so we're going to use the trapezium rule. We're going to draw a series of trapezia or even a triangle here and find the area underneath each shape. Okay, so section A, it's a triangle, so base times the height divided by 2 give you 5 times 22 divided by 2, 55. Sections B, C and D are trapezia. That means to find the areas, you need to add the parallel sides, then divide that by 2, and multiply by the distance between them, the perpendicular distance between them. So for section B, for example, the parallel sides are 28 and 22. Divide that by 2, and times by 5, and you get 125. Okay. Similarly for C and D, the answers are there. And then the total distance travelled in those 20 seconds is given when you sum those values up. That's 497.5 meters. Okay, that is 3 marks for that part of the question. Now part B asks us, is the answer to part A an underestimate or an overestimate of the actual distance the car travelled in the first 20 seconds? Give a reason for your answer. So if you look at the way I've drawn my diagram, I've shaded the areas underneath that curve, which I've not actually calculated in my answer for part A, right? Since I've drawn a triangle here, the triangle is the area which is not shaded in blue, right? So this distance travelled here, which I've shaded in blue, is not part of my calculation. Similarly for section B and section C, and section D will have a very small section as well, right? And that's a limitation of the way I've modelled this using the trapezium rule. Okay, so in other words, my answer is going to be an underestimate, since there's a part of an area here and here which I've not included in my calculations. Okay, and that's what you get when you're estimating. So my answer is it's an underestimate since the shaded region is not included. So the whole question there is worth 4 marks. Question 13. Another speed time graph. Okay, so you can see here you've got speed on the y-axis and time on the x-axis there. Okay, and part A asks us to find an estimate for the distance the car travelled in the first 10 seconds. Okay, use 5 strips of equal width. So this is similar to the last few questions in this booklet. Okay, what I'm going to do is I'm going to use the trapezium rule. Okay, I'm going to draw a series of trapeziums and triangles. Okay, within the first 10 seconds, and since I'm using 5 strips of equal width, that means that 10 seconds divided by 5, each strip is going to be 2 seconds wide. Okay. Then I'm going to find the areas underneath each of those strips. So it looks something like this. So I've got 1, 2, 3, 4, 5 strips. Okay, I'm going to find the areas underneath each strip, and that would give us the distance the car travelled, since speed times time equals distance. Okay, so for the first section, section A, well, that's just a triangle. So the area of a triangle is given by base multiplied by height divided by 2. So that would give us an answer of 2. Section B, C, D, and E are all trapezia. To find the areas of a trapezium, what you need to do is you need to add the parallel sides, divide that by 2, and multiply by the perpendicular distance between those parallel sides. So for section B, for example, this parallel side is length 5, this parallel side is length 2. If I add those together and then divide by 2, and then I multiply by the distance, the perpendicular distance between them, which is 2 seconds. So that would give me an answer of 7. I'll follow the same step for each of those sections there, and the total distance it travelled in those 10 seconds is given by the sum of all of those areas, which in this case is 86 meters. So that's 3 marks. Part B. Is your answer to part A an underestimate or an overestimate of the actual distance? Give a reason for your answer. There's a similar question to the previous question we had on question 12. So what we notice with this curve here, if I'm applying this trapezium rule, if you look really carefully here, I've shaded in blue parts where I'm actually working out an extra area using these trapezia and triangles. Okay, so for example, it's a bit clearer on section D. If I'm finding the area of this whole trapezium on section D, I'm actually including an area which is not underneath the curve. So my estimate here for section D, for example, is going to be slightly too high. And it's similar for A, B, C, and E, right? There's going to be slightly too much area which I'm including in my calculations. So my answer to part A is actually an overestimate, since the shaded region is also included. That's why I've shaded that region there. You don't have to shade it on your diagrams in the exams, but I've just done it for illustrative purposes. So that whole question there is 4 marks. Question 14. Here's a speed time graph showing the speed in meters per second of an object t seconds after it started to move. So again, like the similar questions previously, we've got speed against time. Okay, speed against time. Part A states to find 3 strips of equal width to find an estimate for the area under the graph between time 1 seconds and time 4 seconds. So in this region here between 1 and 4, you need to find an estimate for the area. Okay, and it actually says it's under the graph. So the area we know is given, the area under the graph gives us the distance, right? So what we're going to do is essentially we're going to find the distance between time 1 and 4 that this object travels. So this is how we do it. So it says to use 3 strips of equal width. Since there's 3 seconds between time 1 and 4, each strip is 1 second wide. So we're drawing 3 trapezia underneath this curve. So we use the trapezium rule. Okay, so I'm going to find the area of each trapezium. To find the area of a trapezium, what I do is I add the parallel sides, I divide the answer by 2, and I multiply by the perpendicular distance between the parallel sides. So for section A, for example, this parallel side has got a length of 6.3. This parallel side's got a length of 3.5. I add those together, divide it by 2, so in essence I'm finding the mean average of these 2 sides, and I multiply by the perpendicular distance between them, which in this case is 1 second, and that gives me 4.9. I'll repeat that process for sections B and C, and the total area underneath that graph between time 1 and 4 is therefore the sum of these 3 numbers, which in this case is 21.15. You don't actually need units here. I've included the units because this sort of gives us a clue for the next part of the question. Part B, describe fully what your answer to part A represents. Well, what we're doing here is essentially, because we're finding the area underneath this graph, we're doing speed multiplied by time. Speed multiplied by time gives us the distance. So think back to that formula of speed equals distance divided by time. Speed multiplied by time gives us distance. So in essence, we're finding an estimate of the distance travelled in that 3-second period. Okay. Part C. The last mark in this 6-mark question. Explain whether the answer in part A gives an underestimate or an overestimate for the area under the graph. Well, the answer in part A is actually an underestimate. The reason being, when I'm using trapezia on this graph here in particular, I find the area underneath that section there for A. That doesn't include this area which I've shaded in blue, right? So my area which I've calculated here is actually slightly too low. Similar for section B. I haven't included this area shaded here. That's a limitation of the trapezium rule. It will only ever be an estimate when you've got a curve. Sometimes it's an underestimate, sometimes it's an overestimate. It depends on how the curve is. So that's the answer for part C. The whole question there is worth 6 marks. Question 15. Here's a speed time graph for a train. So it's a speed time graph similar to previous questions here. Work out an estimate for the distance the train travelled in the first 20 seconds. Use 4 strips of equal width. So the distance the train travelled is given by the area underneath this curve. Since speed multiplied by time gives distance. So you need to find the area underneath this curve. And it says to use 4 strips of equal width, and we're doing it the first 20 seconds. So 20 seconds divided by 4 strips means that each strip will be 5 seconds wide. So in a sense, doing this. So here's 4 strips, 5 seconds wide. And so each strip here is in the shape of either a trapezium, or in this case here, just a simple triangle. So when I find the area of each of these shapes, that gives me the distance that has been travelled by this train. So for the first shape here, this triangle, the area of a triangle is just quite simply the base times the perpendicular height divided by 2. So the base is 5, perpendicular height is 2, divide that by 2 and you get 5. For sections B, C and D, well, these aren't triangles, these are trapezia. And to find the area of a trapezium, you add the 2 parallel sides, you divide that by 2, then you multiply by the perpendicular distance between them. So in this case here, it would be 5, add 2, divided by 2, multiplied by the perpendicular distance, which is 5. You follow that same process for sections C and D, and the total distance that the train travelled in those 20 seconds is given by the total of these 4 numbers here, which is 130 meters. Part B, for that last mark, it asks whether our answer is an underestimate or an overestimate of the actual distance the train travelled. Since we're using the trapezium rule here, okay, I'm finding the area underneath this curve. But since the curve is curving upwards, I'm actually finding a slightly larger area. So I'm actually finding, this is the trapezium, I'm actually finding the area of. It includes this small region here above the curve. Similar for section C and section B, and potentially even section A. So the area I'm actually finding is slightly too large. The train will have travelled slightly less distance in real life. So my answer is an overestimate, since the shaded region is also included. You don't need to draw these shaded regions on your graph in your exam. I'm just doing it for illustration purposes only. The whole question there is worth 4 marks. Question 16. So this graph shows information about the velocity in V of a parachute t seconds after leaving a plane. Here you got a velocity time graph. Okay. So part A, work out an estimate for the acceleration of the parachute at t equals 6. Okay. Since this is a velocity time graph, the acceleration is defined as the rate of change of the velocity. In other words, how much the velocity changes at a certain point in time. And since that is given by the gradient at a relevant point in time, if I find the gradient at time equals 6 here, the gradient at this point, then that would give me an estimate for the acceleration. To find the gradient, I need to draw a tangent to this curve at this point. So that's what I'm going to do now. Here's my tangent to my curve. Okay. So when I've drawn this tangent, I then treat that as a hypotenuse of a right angle triangle, because I need to find the gradient of this tangent. To find the gradient, it's a change in y divided by the change in x. Your right angle triangle can be as big or as small as you want it really, but the bigger it is, the more accurate it's likely to be. So the rate of change of y with respect to x. Okay, so the height here is 60 subtract 21.5, and the width here is 9.5 subtract 0. So if I divide those two values, the change in speed, which is the y distance, divided by the change in time, which is the x distance, that gives me 4.1 meters per second squared. That's for 2 marks. Part B. Work out an estimate for the distance travelled by the parachute in the first 12 seconds after leaving the plane. So I've done this in a different colour here just to show that's a different part of the question. So section A here is a triangle, section B is a trapezium, and section C is a trapezium. If I find the areas of these 3 sections, that will give me an estimate for the distance fallen by the parachute, since the velocity times time gives displacement. In other words, it's the distance. Okay, so find the areas of each of these sections. To find the area of a triangle, it's the base multiplied by the perpendicular height divided by 2. That gives me 70. To find the area of a trapezium, I add the 2 parallel sides, I then half the answer, and then multiply by the perpendicular distance between them. So for section B, for example, it's going to be 172. Section C is 210, and the total distance fallen by the parachute in those 12 seconds is 452. It's the sum of these individual distances here. So the whole question there is worth 5 marks. Be sure to check out the other clips on linear graphs and advanced linear graphs in the algebra section of my YouTube channel, and also check out the PDF booklets on mathsupgrade.co.uk for further support.